So one thing to be just careful of when you're using this Newton-Raphson method is that if you choose a point too close to the critical point, what can end up happening is you can end up having a long time for that point to hit the x-axis. Okay, so the closer you are to the critical point, the more horizontal it is and takes a longer time to hit the x-axis. So if this is your first approximation, what ends up happening is your second approximation can end up being over here. Okay, and then your third approximation, okay, using that critical point, could be way over here. And now notice that physically what will happen is it's not going to focus in on this root, but it's going to start focusing in on another root somewhere over here. So you have to be a little bit careful in that you want to be fairly close to the root, as close as you can, and you don't want to be too close to a critical point because that can affect your results as well and sometimes it just takes longer to focus in on the solution. Sometimes it will entirely miss the solution, find other solutions. Okay, so let's apply this in this case. So we're going to solve for, we're going to approximate pi because we're going to actually solve this equation. When f of x equals 0, tan x must be pi. So what we're going to do is we're going to approximate pi using this equation here. So I'm going to set this up as tan x. So tan x equals 0. Okay, and so my derivative, so y prime is going to be equal to secant squared x. Okay, so then setting up my Newton's method, my formula, n plus 1 is equal to xn minus f of x. Okay, so tan of xn divided by secant squared of xn. Okay, maybe we could just simplify this a little bit because we can say that xn minus, this is going to be sine over cos, and this is going to be cos squared. So secant squared is cos squared in the numerator, and we can actually get rid of one of these. Okay, so we end up with this little bit simpler formula: sine xn cosine of xn. Okay, so then I'm going to start with x1 is equal to 3, and I'm going to use that formula then to calculate x2. Okay, so punching this into my calculator, and I get 3 minus sine of 3 cosine of 3. Okay, and my first iteration gives me 3.1397. Okay, so notice that it is getting closer to pi dot 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 dot. Okay, and then as I reapply this formula, okay, I do it again, I'm going to get 3.14159. That's already, even with just 2 iterations of this, I've already got the first 6 digits of pi. Okay, 3.14159. This is 2 dot 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 dot. So this is very quickly focusing in on the actual solution. It's actually a very efficient method to use. Okay, because if once you start getting kind of close to the 0, you will get a high degree of accuracy within a few iterations. Okay, so this is another example here. So we'll try this one here. So we're going to start with, we're going to try to solve this equation. So again, notice that this equation cannot be solved algebraically, okay, because it's an x outside the log, x inside the log. Okay, so I'm going to set my y equation as y equals x plus log x minus 2. My y prime then becomes 1 plus 1 over x. Okay, and then my formula becomes xn of y over y prime. Okay, now if you want to simplify that, you can, but we're just going to leave it like that. And let's estimate a whole number solution. So if I use 1, I'm going to get 1 plus log 1, which is 0. Let's get in there. 2 plus log 2. Maybe we'll try 2 plus log 2 because that's going to be maybe slightly closer. So either 1 or 2 would work. So I'm gonna use x1 is equal to, well, let's just use 1. 1's much easier to calculate. Okay, so then I'm gonna start with my 1. Okay, so I'm gonna do 1 minus 1 plus log of 1 minus 2 divided by 1 plus 1 divided by 1. Okay, so I get an answer. My first iteration is going to be, looks like it's 1.5. So at x equals 1, or x equals 2, or n equals 2, my x equals 1.5. So that's my first iteration. Okay, so I'm going to do that again. And as I do this again, I get 1.5567 or something. Okay, so x3 equals 1.5567 dot 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 dot, and I can see that, you know, based on my calculations, I've got a very high degree of accuracy after that iteration. So even this one here, I'm not going to get very much more accuracy. I'm going to get 1.557145576. Okay, and you don't need to go to all these. I think it's just said 4 iterations, so 1, 2, 3, well, 4. There's my 4th iteration. It's quite accurate because basically I'm going to have the same degree. I'm going to have 8 digits, decimal places of accuracy. Okay, so that, notice that only differs in the 9th decimal place spot. Okay, so we have a very high degree of accuracy with this when we apply this formula.